Hello once again, and welcome back to our look at trigonometry. This time we're kicking off a new unit. We've wrapped up the basics of analytic trigonometry. We've got the basics of showing things are identities and simplifying expressions. And we've also got some basic formulas. We've got the sum formulas, the different formulas. And now the time has come for us to continue down that road as far as we can. Trying to show as many equations that we can are identities. And then from there, we will start to work with equations that aren't necessarily identities and figure out where they are true or not true. So here is pretty much all that's on our docket for the rest of this course. First of all, for the next week or so, the next week or so, we will start adding on more formulas. Double angle, half angle, power reduction, sum product, product sum, all of those, and we will use all of those to produce exact results and show that things are identities. And then from there, we will stop with identities and start looking at still more general trig, still more general equations, and try to find solutions that aren't necessarily everything. And once we've exhausted that, once we've reached the bottom of analytic trigonometry, we will start to look at other coordinate systems and kind of extend the idea of trigonometry, of circular rotation, into other systems. So this is kind of an interesting moment in time for our course because we've kind of reached the end of just triangles and circles, and now we're going to be as general as we possibly can. So let's get to it. Because some of you may be wondering, why do we even bother? Why more formulas? Why more of any of this? Well, here's an example. Here's something to get us going here. Suppose we have some angle theta, and we don't know exactly what it is, but I do know it's in the second quadrant, and I know that sine of that angle is 4/5. So what is the sine of double that angle? What is the sine of 2 theta? And surely we'd be able to crank that out, right? We've got theta. We know that rotation, such as it is for the ratio of opposite to hypotenuse for the resulting triangle. So surely we would be able to find sine of 2 theta. And at the same time, it's not as easy as it looks. It's certainly not the immediate, obviously wrong answer, which is I factor out a 2 out of the sine, which we just can't do, right? Sine of 2 theta is not 2 sine of theta. In the same reason that you can't distribute sine across an argument, you can't pull things out of an argument. Sine of anything can't be 1, and so this approach is clearly false. We have to do something else. We have to have more formulas. That said, though, we don't necessarily have to have more formulas if we don't care about exact answers. Right? If we don't care about exact answers, if we allow for rounding error to creep in, then we can use a calculator to find arcsine of 4/5. We'll get about 53.1 degrees. And so recognizing we're in the second quadrant, the corresponding angle theta is 180 minus that. It's 126.9 degrees. And so I double that, get 253.8 degrees, find the sine of that, and get negative 0.9603 from the calculator. But what if we want to compute it exactly? This is an approximation. This is, at best, an approximation. So to get an exact answer, we need more. And what that more is going to be is to recognize, 2 theta, that's theta plus theta. I use my sum formula for theta plus theta, sine, cosine, cosine, sine. Everything's equal, so it adds together to be 2 sine theta cosine theta. Now here's one problem. And that problem is, I know that sine of theta is 4/5, but I now need cosine of theta. And the way we're going to do that is with triangle substitution. I know that for my theta, my sine of that angle is 4/5. So for this to be a right triangle, that last side has got to be 3. But we are in the second quadrant, so that's in the negative direction. So cosine of theta, if sine of theta is 4/5. Cosine of theta has to be 3/5, but negative because we are in the second quadrant. So putting all that together, we're finally able to say sine of 2 theta is negative 24/25, or negative 0.96 exactly. In fact, we can do this same approach for all the double angles. We can do sine of x plus x. We can do tangent of x plus x. All right, sine of x plus x gives us 2 sine cosine. Tangent of x plus x, or tangent of 2x, gets us 2 tangent over 1 minus tangent squared. And then lastly, cosine of 2x is a little special, because after you do the sum formula for cosine, you're looking at cosine squared minus sine squared of x. And we've got the Pythagorean identities at our disposal, right? Sine squared plus cosine squared equals 1. So that means I could substitute 1 minus sine squared for cosine, getting me this equation, this form right here, 1 minus 2 sine squared x. Or I could do it the other way, substitute sine squared out, and end up with 2 cosine squared x minus 1. All three forms here are acceptable forms for cosine of 2x. And we use these forms to do a number of things. One thing we can do is we can, as we've been doing, right, use them to compute more and more exact values. Also, we can use them in proofs and identities and those sorts of things, and I'll show you that here in a second. But let's try and find the exact value of sine of 2 arcsine of 1/5. Let's try and find the sine of 2 arcsine of 1/5. Well, this is at the whatever angle arcsine of 1/5 gives us, that's just an angle, so I'm looking at 2 angle inside a sine. I need to use the double angle formula for sine. So sine of 2 angle becomes 2 sine angle cosine angle. And once again, we kind of have to stop and think, okay, well, what is my sine and my cosine going to come out to be? And so whatever, and this ties into inverse trig as well, right? Arcsine of 1/5 is asking, well, what is the angle that gives me sine of that angle being 1/5? And I don't actually need that angle, I just need the sine of that angle and the cosine of that angle. So once again, we'll draw us a triangle, do some triangle substitution here, right? Whatever angle theta this is, sine of this angle is 1/5. So sine of the arcsine of 1/5, that does produce 1/5, because whatever angle this is, the sine of that angle is 1/5. And so what we have left over is, by the Pythagorean theorem, let's see, 5 squared equals 1 squared plus this side squared, that's 25, that's 1. That leaves 24 inside a square root. So the cosine of this angle, the cosine of arcsine of 1/5, is root 24 over 5. And we combine all of that, and we're able to say sine of 2 arcsine of 1/5 is 2 times 1/5 times root 24 over 5. And that altogether is 4 root 6 over 25, or 2 root 24 over 25. And that's how we do this. That's how it's done. So I'll leave this for you here. I want you to take a minute and decide how to go about cracking cosine of 2 arcsine of 1/5. Because remember, there are 3 different forms you can choose for this, and one of them actually makes your life pretty easy in comparison. So do take a minute, try and compute cosine of 2 arcsine of 1/5. Tell me what you get, and I will see you on the other side. And we're back. And let's see, we have 3 forms to choose from. But also, right, arcsine of sine, or sine of arcsine, is the nicest to deal with. So let's look with this form, 1 minus 2 sine squared of x. Doing that, we've got 1 minus 2 sine squared of theta. And so 1 minus 2 sine of arcsine squared, so 1 minus 2 times a fifth, quantity squared. Cosine of 2 arcsine of a fifth is 23/25. And that's it. The other forms you could have chosen would have gotten you here as well. There might have been a little more computation. You would have had to deal with squaring the root 24 over 5, but it would have gotten you here as well. And so yes, we can use these formulas to compute exact values of things that we would not have otherwise been able to compute. Which is nice. Very nice indeed. But that's not all we can do with them. All right, one last idea I want to leave you with here for this video is that you can also use them in proofs. Use them to verify things are or are not identities. So for instance, suppose I wanted to show the equation 1 minus tangent squared x is equal to cosine of 2x over cosine squared of x. Well, I can do that now. By recognizing I've got a cosine of 2x on the right-hand side, I could use a double angle formula for that and try and finagle it to work out to be 1 minus tangent squared x. The one issue with that might be, again, cosine of 2x, there's 3 forms to choose from. I might have to stop and pick the one that works out the nicest. The others will work as well, but more substitutions might be required. So kind of backing away from that, not necessarily recognizing what substitution to use for cosine of 2x, let's instead start with the left-hand side. 1 minus tangent squared, that's 1 minus sine squared over cosine squared. That's, after we combine our fractions, cosine squared x minus sine squared x. And we kind of flip back here. Oh yeah, that is an acceptable form of cosine 2x. So that is cosine 2x over cosine squared x. That is the right-hand side. And you see this is reversible. We could start with the right-hand side, do that same substitution for cosine 2x, and work back to the left-hand side. So this does verify that our equation here is in fact an identity. And that is the long and short of it. That's how we can use our double angle formulas. So that's it for now. We got one more coming up on the half angle formulas. So we'll get those introduced. I will see you then.